you. So we will start slowly. And please do call me Martin, because when you ask questions and you say, Professor, I have a question, then I have the impression I have to be able to answer. Okay, so today we will continue from yesterday. So yesterday we discussed these two things. So the first one was we introduced the Friedman, Lemaitre, Robertson, Walker cosmology with the isotropic and homogeneous metric, and we looked at the link between the evolution, so the expansion of the universe, and the content of the universe. And we said the universe is expanding. Okay, so one consequence is that it was smaller and hotter in the past. And with the help of age measurements, it looked that we found some suspicious numbers. And then with distance measurements, we found that we need not only, through this link, that we need not only matter, but we also need something to make the universe accelerate that many times. And for that, we use this cosmological constant lambda that we introduced earlier, based on Einstein's recommendations. And so specifically, just to remind ourselves, the constraints that we have, where I will discuss what the data is. I will discuss that a bit later. So, but you should know what the omegas are. So that's the relative density in matter relative to the density that makes the universe flat, and the relative density of this cosmological constant. And you can see that for the best data combination, need about 30% matter and 70% cosmological constant. And then if you look closer, which we can't do right now, but we'll be doing later, we find that about 5% is normal matter and 95% is something else. And that's of course a bit weird. And if you think that starts to look like epicycles, you're not alone. But we don't have a better model. So anyway, so that was, and the universe is very close to flat. That's another lesson. And so that's roughly where we were today. And so that's like the inference on the age of the universe is 13.8 million years. Billion years, sorry. So that's the main takeaway from yesterday. And so then if this was a cosmology course, then I would actually do exactly what I'm going to do now. So then I say, well, the fact that the universe is flat is a bit strange. We briefly said it, I will say it again. And so there are some other problems because the universe is not perfectly isotropic and homogeneous. We are standing on a fairly dense block of material, so where does this actually come from? And some other things. So this is about perturbations, and so I will start to talk about inflation. And so even though this is not really the topic of the lecture itself, it is nonetheless not lost time, because inflation you can think of as an early acceleration. And so the tools that we need for inflation are exactly the same tools that we will use later on for dark energy. And so bear with me. But still it's good to know about it. And then that will also allow us to talk about perturbations, and perturbations are important because the amount of information that we can get from looking at the what we call the background, so that's what we talked about so far. So the homogeneous and isotropic universe is relatively limited, and if we really want to study models in details, then we will have to look at the perturbations. Okay, and then after that, so up to here it's pretty much still introduction, even though we will start to see material that we really need later on. But then we will actually talk about dark energy, and so we will start with the cosmological constant problem. So why are we not happy with this model that fits the data so perfectly? And then we will start to discuss, okay, what can we do that isn't dark energy? So today we probably don't quite get to dark energy, except that here we are actually discussing dark energy, just with a different name. But nonetheless, it's a fairly ambitious program. That said, please do ask questions. I prefer not to get all the way to the end and to tell you something that is actually interesting for you, rather than talk while you play with your phones. Okay. I think I'll pretty much skip that, but maybe just for context. Okay, so yesterday we talked about the smooth shape. Today we will be strongly concerned with what happens here, and then with the creation and evolution of the not so smooth stuff inside. I mean, okay, this is a schematic picture, and a little bit about this object. Okay, and so at some point, people started to wonder, why is our universe so close to flat? And we calculated yesterday, based on the Friedman equation, we calculated the evolution of the deviation from flatness. So this is absolute value of the total density minus 1. So if this is 0, then the universe is flat. And this evolves like minus a double dot. And we saw that a double dot, so the acceleration is negative for normal stuff, and so this is positive for normal stuff, and hence the universe should become less flat. But we also saw that the data tells us the universe is flat to better than 10 to the minus 2, nearly 10 to the minus 3. And so this is bizarre, no? Because if you go back in time, the universe becomes more and more flat. And actually, let me just to show you beyond that why this pretty much has to be. Well, I'll do it. Oh no, here's the black one. So you can think of, we can go back to the evolution of the energy densities with the scale factor. So does someone remember how the matter density evolves with scale factor? Yeah, exactly. A to the minus 3. And radiation. A to the minus 4. So this is dilution with volume, and this is dilution with redshift. Okay, whoops. And radiation adds this 1 over a squared term. So you can associate the kind of energy density with radiation that go, because here you have the energy density, and so you can think of this as an energy density of curvature. And so this one goes like a to the minus 2. Okay, that's a bit overdoing it now, but so if this is not too low, it will eventually dominate. No, that's what this says. And so this has to be very low. And so the question is a bit how low, and so early on it has to be extremely low, like because we know that this has to be somewhere down here, and so if we go back it goes down, more down, more down, more down. And so basically at Big Bang nucleosynthesis, so energy of a mega electron volt, physics that we think we understand very well, the universe had to be flat in 1 in 10 to the minus 16. And if you think you can go back to Planck, okay, that's not really very realistic, but in that case it would have to be 10 to the minus 16. But okay, so such small numbers normally need some kind of explanation, but you can say initial conditions, okay. But it's nicer if you have a dynamical way to create this. And so what would be a way to do that? If you want to make the universe more flat rather than less flat, what would you have to do? So if you want this to be decreasing rather than increasing, so you have to make a double dot positive, and so you need to accelerate the expansion of the universe. And if you have something that accelerates the expansion of the universe, then the universe will become more flat. Okay, but that's maybe just a curiosity now. But there are also other problems. I call this here, why is the sky uniform? Because that's the traditional way to put it. I will tell you afterwards actually how this is a better way to think about it, but I won't show you the data right now. So let's, for a moment, let's actually look at this thing here. So we observe the cosmic microwave background. So this is effectively a picture of the universe at recombination. And so T0, the age of the universe now is 13.8, was it? billion years. I cannot remember 3 slides into the past. Recombination is some 380,000 years. So this one is much, much less than that. So it's much closer to the Big Bang. And so then you can ask yourself, well, how big is the region that I can see in the CMB compared to the size of the causal horizon at the moment when the CMB was created? And so you can calculate it. So that's the calculation that we already did. So light moves on what is called a null geodesic. ds square equals 0, and ds square was minus dt square plus a square. Let me just write it. It's simply typed like this. And so I can, let me call this the r square, just because I call it r there. So I can simply calculate so if this is 0, then I have dt square equal a square dr square, or r is integral dt over a. Okay? And then you need to know, how does a actually evolve with t? And for that, you go again to how does rho evolve with a? And so you go to, and then you go to the Friedmann equation. Proportional to rho, and rho goes like a to the minus 3, 1 plus w. Okay, and then you have now a differential equation for it. So you have dA by dt, and so you solve this differential equation, and you find that a of t goes like t to the 2 divided by 3 times 1 plus w. Okay? And then if you calculate this for matter domination, for example, just for simplicity, you find that the distance from, so this distance here is about 3 times T0, because T-rec you can basically take 0, it's so small. But you also find that the distance from 0 to T-rec is the same integral, and it's much, much smaller, except when is this not small? I mean, just fundamentally now, without looking at W at first. Well, it's not small if the integral doesn't converge. Now, if a of t goes like t to a small power, then the integral converges, and then generically this is much smaller. But if this is, for example, t, then the integral doesn't converge, and then it's arbitrarily large. And when does the integral converge? Well, it converges if w is larger than minus 1/3, and it doesn't converge if w is smaller than minus 1/3. And so if the universe very early on is filled with normal matter, then, so where w is positive, then this distance here is indeed much smaller than that distance. But if the universe is filled with something funny that has a negative pressure, and the condition is exactly the same, so that the universe is the expansion is accelerating, then this can become arbitrarily large, and so you don't have any problem with this. So you can say, well, why do I care whether the sky is uniform? Isn't that just also initial conditions? It's actually a bit more, because we actually see correlations in the cosmic microwave background over this distance. And so to make correlations over this distance, you need them to be in causal contact. And so my thesis topic was topological defects. Never mind what they are. But this was a mechanism that where you had some evolving stuff creating perturbations, And this thing totally rules out, the fact that we observe this correlation totally rules out any mechanism like that. So effectively you need something funny here, otherwise you simply cannot explain the observation. So this, in my opinion, is actually one of the strongest observational results supporting the very strange model that we are now led to. So the model that we are led to is that we can solve all of these problems if A double dot is positive sometime in the early universe. Okay. And so what does this mean? A double dot positive, this means pressure, so W less than minus 1/3, or a sufficiently negative pressure. And so we could do that with the cosmological constant, okay, because then P is equal to minus rho, and if in the early universe we have a sufficiently large cosmological constant, then that can do it. But there is a problem, of course, that's if we have a cosmological constant which is constant, and if it is sufficiently large, no, then it will become larger and larger relative to everything else, because as the universe expands, everything else is diluted away. And so you will never stop inflation, well, let's call this inflation. So you will never stop this accelerated expansion, and you definitely don't end up with the universe that we observe today. And so we cannot use the cosmological constant. And so we need to use something else. And so when you ask theorists, well, use something else, they say, well, we could use some field. Well, what's the simplest field? Let's use a scalar field. Until not so long ago, I can then make the joke, because we have seen so many scalar fields. Okay, now we have seen one, the Higgs field, and actually there are models that use the Higgs field to do that. Okay. And so now the slide that I will show again tomorrow, because if we can use a scalar field to make the universe expand early on, you can use scalar fields to make the universe expand now, again in a way that's accelerated. Okay, and so how do we insert the scalar field in cosmology? So then we use an action-based formalism. And so I hope you have all brushed up on your variational calculus and your GR, action formalism for GR. So what we do is we say that the action, the total action for the universe is the gravitational action and the matter action. And for matter here I put in the scalar field, and we can simply add them. And the gravitational action is called Einstein-Hilbert action, and is simply given by R. And this is the action for a scalar field that you had in your quantum field theory classes, or your classical field theory classes, because today I'm not explicitly doing quantum field theory, just classical field theory. Okay. And then if you have an action, what can you do then? Well, it's on the slide, but just generally, you can calculate equations of motion. And you calculate an equation of motion by doing a variation with respect to the dynamical degrees of freedom. And so what are the dynamical degrees of freedom? Well, for the scalar field, it's the field, phi, and for gravity, it is the metric. Okay, and so if you want to have the gravitational equation of motion, you do the variation of the total action with respect to the metric. And what is the gravitational equation of motion? We already saw it. It's the Einstein field equation. And so if you calculate this variation, you find exactly the Einstein equation, where the variation of, well, you have to be careful, you have to keep this in, so the variation of this term gives you the Einstein tensor, and the variation, so the variation of this and the variation of the field then has to give you the energy momentum tensor. And so you can actually use this to define your energy momentum tensor. And so effectively you can just calculate this variation, and then you look, now I wiped it out, but you just look what is in my T00. If I calculate this for mu0, nu0, then I have to find rho on this side, and what you find is this expression. And in the II part, so the diagonal, well, I have to find P, and you find this. And so tomorrow I give a few extra hints how to calculate this. And I will actually ask you to calculate this one, because this one is easier to calculate. And that one, there are a few subtleties to deal with that. And yes, and so you get the scalar field equation of motion by calculating the variation of this with respect to phi. And if you do it with a metric that is, so this here is again background, so here we take the metric that is Friedman, Lemaitre, Robertson, Walker, and here as well, and then you find this equation of motion. And this is effectively, if you are a theoretical cosmologist trying to invent new dark energy or modified gravity models, you write something else here and you calculate that, and that's pretty much what you do. So okay. And so this is really the general approach. And now, okay, once we have done that, we want to know what is the equation of state of the scalar field. Can it do what we want? Can it accelerate the expansion of the universe? And so for that we have to take a closer look at these two functions. And so I wrote them here again. And so let's look at two limits. Actually, let's start with this one. So if phi dot, if the time variation of the field is large, what is the relation between pressure and energy density? Sorry? If phi dot is large, right, then now the phi will vary in general. Now because the phi is the field, and the field will vary as a function of time. So since we only look at the perfectly isotropic and homogeneous case, nothing here can be a function of space. So, but the phi is a function of time. The field can evolve in time. Actually, let me just go back. Let me actually, oops, that was the wrong way, because then actually because of this I want to go. So okay, what am I actually talking about here? Right, so as I said, the phi is necessarily a function of time here if I only look at the isotropic and homogeneous limit. Okay, and how does phi evolve as a function of time? Well, this equation here is actually, you can think if I call phi x instead of phi, and you think of this as an x of t, and so as an evolution of a particle, if I then the equation x double dot plus something times x dot plus gradient, let me call it gradient, well, let me call it dx. The gradient dxv equals 0. What kind of equation of motion is that? I mean, okay, this is just a normal equation of motion for a field that is in a potential. No, the field for a particle that is in a potential. So the gradient of the potential accelerates the particle, and this here is a friction term. And so the field here in the homogeneous limit follows exactly the same equation of motion as a particle in a potential, and the expansion of the universe acts as a friction, because as the universe expands, the particle can slow down in its time evolution. And so if you have some potential v, this is v, this is phi, and you have your phi of t here, phi of t will just roll down the potential like any self-respecting particle would. So that's what this equation tells us. Okay. And so that's why it makes sense then to ask, what is phi dot? Phi dot you can think of as the velocity of the field, like x dot. And so if phi dot is large, so the field moves rapidly, then what is the equation of state? So large in the sense of you can forget about the potential contribution, and you only have the phi dot square that dominates the energy. So you can think of this as a kinetic energy dominated contribution, because if you look at this is exactly also like a particle. No, this is v squared contribution, so this is the kinetic contribution, and this is the potential energy. So it's really exactly, everything here is like a particle in a potential. And so if you are kinetic dominated, what is the equation of state parameter? 1. Because you can neglect this, and so P is equal to rho, and so W is 1. Another more interesting case for us, if you are potential dominated, which is called slow roll, so if the field evolves slowly, it moves slowly, so phi dot is small, what is the equation of state then? -1, exactly, because it's okay. And so the particle can move between, so for a scalar field, the equation of state can then be somewhere between -1 and 1, and it can change in time, depending how fast the particle moves in its potential. The field moves in its potential. Okay. So if it moves fast, then it has a very large W, and so it will actually not. It will kind of try to slow down the expansion of the universe, and if it is moving very slowly, then it starts to accelerate the expansion of the universe. And so by drawing a potential that you like, you can do pretty much what you want. And of course, if this works in the early universe, it can also work in the late universe. So even though I'm explaining you here inflation, I'm also explaining to you one of the models of dark energy. And in inflation then, I just quickly go through that because I will make a remark about it later. In inflation, we want this part here that is called slow roll, and so then one often neglects the phi double dot, right? In the equation of motion, there was a phi double dot, and then I neglect it, and in that case, I simply have that h phi dot goes like the gradient of v, and this is the Friedmann equation, and so then you can easily now look at you can easily see that the phi dot squared then let me see. Let me think a moment. Now the phi dot squared goes like the v prime, and then this I can write, so the phi dot squared goes like v prime squared, and using this parameter I can write it as epsilon times v, and then I insert that into the p, and so I have 2/3 epsilon from the phi dot squared minus 1 times v, and that gives me then the equation of state, and so I can see then that as accelerated expansion I need to have that this epsilon that p is less than minus 1/3 rho, and that then means that this slow roll parameter is less than 1, and that tells me something about the shape of the potential. But that's slightly a side remark that we need later. So that last part you can forget again. Okay. And then just to give you some idea of the kind of potential that people like. So here are some typical potential that people like in inflation. So the original models used something called small field, where you have a flat part of the potential. While the potential is flat, the gradient is small, the particle moves slowly, and the universe inflates, and then it drops over the edge. The particle moves faster. When the particle moves faster, the equation of state becomes less negative, because phi dot becomes larger, and so the universe stops accelerating. And then there are so-called large field models, chaotic models, typically of the type phi square or phi to the 4, where the particle moves down, and while it is high up, the friction slows it down, and in this part it moves slowly, and as it rolls down, it accelerates and eventually stops the expansion of the universe. And then I forgot to get the picture for that because my laptop had an internet problem earlier. There you have like a 2D, so there's like two fields, and in one direction you accelerate, and then you drop over the edge and you fall into a valley, and then the universe stops accelerating. But anyway, so there are many possible models as a function of the potential, and that's another statement I can copy one-to-one to dark energy. You can make many models as a function of the potential in dark energy as well. And in dark energy then we cheat, but we get to that at some later time. Okay, so since I'm actually now telling you about the inflation, well, let me finish quickly the inflation part, because a priori this is a fairly crazy theory. Okay, so if someone tells you about the crazy theory, you should go like, why do we take this seriously? Okay, so typically the answer is because we don't have anything better. but okay, the theory does make some predictions, and that we can actually, I mean, the key question really is, okay, what are the observational predictions, and are they in agreement with data? And so the observational prediction is, well, we have this accelerated expansion that makes the universe larger and flatter. And so is the universe large and effectively flat? Indeed it is, okay? That's kind of why we introduced it, so that it does. Now, another thing inflation does, that I didn't discuss at all, but if you now look at quantum field theory in this background of the expanding universe, you see that a bit like the Hawking effect. You can think of that if you create virtual particles, because the universe is expanding so fast they are dragged away, and so you create real particles. Or you can think of that your vacuum changes, and if you project one vacuum on the other vacuum, you find that it's no longer empty, so you have particle creation. There are different ways to do it. And you can calculate what is the spectrum of perturbation that you create. And that may not make a lot of sense right now, but you create a specific kind of distribution of perturbations. And the one that we observe is exactly that. And actually the one that I calculated for my PhD thesis for defects look totally different. And that actually killed my thesis topic. Just you can as an encouragement for PhD students, you can survive your thesis topic being killed off. Okay? One can also show that depending on the scenario, the statistics of the perturbation can vary, but typically in the simple models they are nearly Gaussian. And so then you can go and check. That was one of the things that the Planck satellite did, and the perturbations are very close to Gaussian. Actually, if they are, it's actually a bit a shame that they are so close to Gaussian that Planck did not see any deviation, because if you see deviations, then that tells you a lot about the actual model that underlies inflation. Okay, and these perturbations, they're created on all scales, including what is naively super horizon because of the argument, and indeed we see them. And the last key prediction of inflation is that all light degrees of freedom acquire perturbations. So not only the inflaton field, which leads to the perturbations that form structure, but also the metric itself, gravitational waves, because gravitational waves are massless, and so they should also acquire perturbations. And so generically you should create what is called primordial gravitational waves. And if you saw those, that would be the missing key prediction for inflation. So that's why everybody is so desperately looking, and that's why BICEP a few years ago had this huge impact. And so this is just a slide to show a bit what we think we know about the initial perturbations. And so this is the amount of gravitational waves. So this is from the cosmic microwave background, because the cosmic microwave background literally takes a picture of the initial perturbations sometime after inflation. So this is the amount of gravitational waves, and this is the deviation of the perturbation spectrum from a scale invariant spectrum. And I don't really want to explain that to you, because otherwise we never get to dark energy. But let's say inflation tells us it should be close to 1, but not quite 1. And indeed, it's something like 0.96. And so you can then look at the large number of inflation models, and you can look which ones survive. So the constraints, the best constraints are these red and blue contours down here. And so one model theorists liked had a potential that goes like phi to the power 4. So this is a phi to the 4 shape here. Phi to the 4 isn't even on this plot anymore. It's somewhere up here. So the next model theorists really liked was phi squared. And phi squared is, I think, this one. Okay, and you can see it's also way out now. All of these actually predicted quite a lot of gravitational waves, and so it's the fact that we don't observe these gravitational waves that kills all of these models. But there are lots of Higgs. If you create a specific inflation model using the Higgs field, that actually lies somewhere down here. It looks pretty much like the green one, I think. Okay, but enough about inflation.
Yeah. Can I ask a question about inflation to end this? So inflation gives us causal origin of perturbations, right? So we have these problems and so on. It made some predictions that, as you said in the previous slides, some predictions that are now confirmed more or less confirmed. But you know, there is a controlled discussion in the literature about inflation, all the alternative mechanisms of the primordial universe. And you said that, okay, inflation is a crazy idea. So can you explain a little more why do you think that? And if they give us what they solve a lot of problems, they give some predictions, and the predictions are being confirmed by observation.
Well, yeah, I mean, if someone comes to you and says, I have a theory about something that happens 10 to the minus 30 seconds after the Big Bang, and the theory says the universe was blown up like a gigantic balloon by 10 to the 60, then you go like, oh yes, no, I mean.
So in this sense,
in this sense, it's like a crazy thing, right? Because it's a theory about the super early universe where we don't really can hope to have direct observations, except maybe for the gravitational waves, which actually are pretty much a direct observation. Because our observations, they're not from 10 to the minus 30 seconds, they're from 400,000 years. So, which still is very early, but a lot less early. So in that sense, it's a fairly crazy idea, but yes, exactly, it solves problems. And I should say there are other scenarios, but because what any scenario has to do, they have to solve the flatness problem, the horizon problem, so that you need to create basically that you need to somehow have correlations on large scales, and they also need to create the perturbations we observe. And basically, the exact implementation of how you do that can vary, but you basically need either accelerated expansion with the scalar field or some other way, or you need to have a collapsing phase followed by an expanding phase, typically going through a bounce. Because really what you need to have the horizon, the co-moving horizon shrinking, and you can do that basically only in these two ways. And so some people then say, I have a different model, like, I don't know, ekpirotic universe, that does it in a different way and much more convincing, and then but then the inflation people say, no, but that's just inflation in a different, with different equations. So, okay, but yes, I think there is effectively, so effectively you need something, basically whatever solves these problems generically does it in a very similar way. Then Then you can write it in different coordinates and call it something else, but there aren't really so many other ways to do that. So in that sense, even though it's crazy, in my opinion, it is a crazy theory, but it's quite well supported.
So about topological effects, you said that of course they don't they need to work for generate the perturbations we observe today, right? But is that completely rule out? I mean,
No.
can we have a small amount of
Yes.
topological defects in the?
Yeah. I think for me, topological defects are now a bit similar to. Actually, I had a slide on it and I took it out, but let me see. Okay, so that's a slide I actually put into hiding, but let me resurrect it. So if you have only a single field slow roll inflation, then you get exactly these things, but then you can have other things. So for example, if you have a multi-field model that you very often, okay, because then of course what you want to do is you have this inflation model and you would like to embed it in some consistent particle physics model, because at some point these should be described by particle physics at very high energies. Okay, and so if you try to invent particle physics model that do inflation, typically you have many fields, and so multi-field models are quite generic then. And, but if you have multi-field models, then also very generically, but you have some kind of phase transition where you go in from one field to another field, and then depending on the exact implementation, but quite often you create topological defects at the end of inflation. And then, and so they are not the dominant source of the perturbations, because otherwise that wouldn't work, but they add some perturbations on top, and so then you can put constraints. And we don't see any, and so we know that they have to contribute less than about 1% of the perturbations that we see, and that puts the constraints on the energy scale of such a transition, and this then rules out this rules out some kind of I don't remember F-term breaking supersymmetric models. Okay, so effectively it's then a bit like this game. That's exactly the same with non-Gaussianity, because also multi-field models are kind of models that break any of these single field slow roll with standard reheating. If you break any of these statements, you do other things like generate typically non-Gaussianity. And so then if you don't see the non-Gaussianity, then that rules out the models that produce too much non-Gaussianity. Of course, it would be much more interesting if we actually observed non-Gaussianity or topological defects, because the non-Gaussianity would tell us a lot, for example, about the kinetic term, okay, because then you can play around with your scalar field actions, so you can put in a different kinetic term, which is also exactly what you do in dark energy. And so the non-Gaussianity would tell us a lot about that, for example. It would also tell us about, like, if there were any curves in the field trajectory. And then strings would tell us a lot about the vacuum manifold at the end of inflation, if we saw them. Okay, so the absence kills models, but the presence of these features would be much more informative. But, somehow in cosmology, it seems to be a bit a standard problem that we're always in the least informative plane. Again, if the dark energy looks like a cosmological constant, the dark matter looks like a perfectly collisionless cold fluid. Inflation looks like the perfect single field slow roll model without any non-Gaussianity, without any topological defects, without any features in the power spectrum, and without any isocurvature perturbation. So it's the most generic thing that's where you have the least information about the physical. I mean, it's like I don't know. It's I mean, I think especially in the technology domain, many people believe that we live in a simulation that has replaced God. I think in Silicon Valley, or you can think of God. So either God or the aliens that simulate us, our world, they were probably quite nasty or a bit lazy, and they just put in the simplest model into the simulation, so they couldn't be bothered to make our world more interesting. And that's actually that's exactly the main problem as well in dark energy modified gravity. So there are lots of links at the phenomenological level between inflation and dark energy. I should maybe say one thing I will not talk about is there actually a link between dark energy and inflation? And so the short answer is maybe. Would make sense. We don't really know. Okay, so I'm not going to talk about this anymore, but that's certainly a very, very good question, but we don't have any information about that. Okay. Good. So much about the early expansion as a first example, okay? And but one of the things I need now are really the perturbations, because so we generate them, so we have them, and we need them, or we wouldn't be here. And as I said, just the background, so the distance measurements, they don't have so much information, but these initial perturbations that we now have, they are going to evolve, and they will evolve depending on the way the universe evolves. And so if dark energy at late time does something funny, they will impact the way the perturbations evolve. And that will, for example, show up in the galaxy distribution, because then we think, okay, where stuff is denser, we form galaxies, and so galaxies should trace the density perturbations. And of course, galaxies also move, and those motion we can see through redshift space effects. I will explain this again later, and so also the velocities depend on the perturbations. The CMB is a direct picture of the perturbations in the radiation fluid very early on, and so of course that also tells us a lot about the perturbations. And in addition, when matter clumps together and becomes denser, then this leads to a gravitational lensing effect, and this we can again use because we can observe gravitational lensing through shape distortion and magnification, like with real lenses, and so that also tells us about the perturbations. So our probes of perturbations, so that's where I could have a complete other lecture about observations, but our probes of the perturbations are actually much more discriminating than just the probes we have of the background. And so that's why these days what we're really interested in are the perturbations and their evolution. That's why at this point I have to say a few things about that. So maybe just for like the background, so when I say perturbations, then you will see symbols, and these symbols now typically we think of them as being in Fourier space, because when we do perturbation, actually maybe this slide I should have put later. Do you mind if I just flip around? Well, maybe not. Okay, I'll tell you now, but what we actually do is we'll see later. Okay. So what we'll see when we calculate the evolution of the perturbations, because the perturbations are small, they're of the order of 10 to the minus 5. And so what we typically do is linear perturbation theory. And linear perturbation theory leads to equations like, I don't know, I'll just write something. So we have some delta, let's say delta rho, perturbation in energy density as function of space and time, delta rho dot equal, I don't know, gradient of the divergence of the velocity field rho of x and t, okay, probably minus. So this would be some continuity equation. If you have stuff falling in, then you change the density. Okay, and these are annoying equations, but we can make them much simpler, because when you have linear perturbation theory, we only have the variables that depend on space and time. They only come in linearly; they're never squared, and so we can then go to Fourier space. And what happens to annoying things like gradients when we go to Fourier space? Yeah, so here they become k's, because when I go to Fourier space, so then I have f of x is some random prefactor times integral f of k exponential plus or minus I k x. Okay, so if I take a gradient here, f, let's say f hat, then this one doesn't depend on x, only the exponential does, and so if I take a derivative here, I get the k down. And so in Fourier space, then this equation becomes something like delta rho dot of k and t equal k dot v of k and t, where this is now in Fourier space. Okay. And these are much simpler equations. No, I prefer multiplications over derivatives. But this you can only do if you have a linear equation, because non-linear products, like a square of v would become a convolution, and then you're really in trouble. And so that's why we will typically work in Fourier space, and so there will be k's all over the place. And so the k, just to say, if you have a co-moving k, and then that corresponds to a physical scale that goes like 1 over k. So small k are large scales, and large k are small scales. Just let's not forget. And then the second point is that if you create initial fluctuations, you cannot predict where an over or under density is. So they're statistically, they're random, and so you need a statistical description. And so that what we do is we use basically they're random and Gaussian. And what describes a Gaussian distribution? A Gaussian distribution function. Yeah, mean and standard deviation, exactly. So here we usually work with zero mean. So the mean is 0, and so we really only need the standard deviation or the variance, and the variance becomes a function of k. So the variance is if you have 0 mean, the variance is the expectation value of the random variable squared. And so you see this is the power spectrum is exactly the expectation value of your random variable squared, except that it's a function of k. It's not just a number. These quantities, because of isotropy, they cannot depend on the direction of k, and because of homogeneity, they cannot depend on the x itself, they can only depend on x minus y, so your 2-point function. And so effectively this means they only depend on absolute value of k. It's a little calculation that I definitely don't have the time to go through, but I'm happy to go through it afterwards if you want. Okay. And so effectively, therefore, what we work with are these power spectra P of k. Or I mean, basically, and when I write something like delta rho, so then typically when I write something like delta rho, I actually mean delta rho of absolute value of k and t, even though usually I don't write it. And you should think of this as really as some kind of square root of the power spectrum of delta. That's quite confusing, I admit. Okay, but now what are actually these equations? How do we get these equations? These perturbation equations. And so that's easy and difficult at the same time. Conceptually, it's quite easy. We say, well, our perturbed metric is the background metric. This is Friedmann, Lemaitre, Robertson, Walker, plus some perturbation. Our energy-momentum tensor is the background tensor, the one that's diagonal with rho minus p minus p minus p, plus some perturbation. And then we stick this into the Einstein equations, and we linearize the equation. Actually, the order 0 gives us back exactly the background equations that you already have, and the linear part gives us the linear perturbation equation. Okay, so that's in principle easy. In practice, whenever you have the Einstein equation, it just becomes long, it has many indices. And there is another problem called gauge freedom that I just mentioned, and then you can forget about it if you don't do cosmology. But you can reparameterize, like GR is fully covariant, so you can change your coordinate system in any way you want, and basically you have 4 directions that you can choose, 4 dimensions, and so you can remove 4 degrees of freedom. And then in addition, just to make it more fun, you can classify your perturbations into scalar, vector, and tensor. And so that's something that you maybe know for a vector field. We can write the vector field as a gradient of a potential plus a pure rotational part. Okay, the potential, that's the scalar perturbation, and the rotational part is a pure vector. And you can do the same for a tensor. And so that's how you end up with scalars, vectors, and tensors. And it turns out that in the metric, if you do all of that, you end up with two scalars that you can, for example, write in this way. And so then you end up with two gravitational potentials. Okay, this do it yourself. That's not fully serious because it is a bit long. And so your perturbed metric, if you keep only the scalars are the ones that are relevant for structure formation. Looks like this. So right before, the Friedman-Robertson-Walker metric, if it's flat, was minus dt squared plus a squared dx squared. So this is the one part. And now we add here two perturbations. These perturbations, I should say now, these are functions of k and t. Okay. And so this is the metric that you use. And then when you calculate the Einstein equations, you find, for example, these, and for the conservation equations, you find those. Okay. And now you see that, okay, so we have the two gravitational potentials. That's the metric side, and on the matter side, so apart from the background, which is rho and p, not sure if I see anywhere a p here actually. And on the perturbations, we have delta rho divided by rho. So typically we don't use delta rho, we use delta rho divided by rho and call it delta. And we have the velocity potential, so the scalar part of the velocity field. And we have something else that is called anisotropic stress. That is in the IJ part of the stress energy tensor. Okay, and of course we have the delta P, the pressure perturbation. So we have four quantities on the matter side and two quantities on the geometry side. And we will go a bit more into that. But okay, is this, now let's see, this equation, can you see what this equation is roughly?
Poisson.
Exactly. So this is the Poisson equation because minus k squared in real space is just the Laplacian gradient squared. And so this is Laplacian phi is delta rho. This is exactly the Poisson equation. And this tells you that if you don't have this funny sigma, the two potentials are the same. Okay. And the conservation equation, so let's see. This equation here, well, this term is small, this term is usually also small, so the main part here is delta, so the prime here is a time derivative. So this is delta dot is minus gradient of the velocity, okay, minus gradient of the velocity. Theorists never can deal with signs. This is exactly this conservation equation that if stuff flows in somewhere, then you have more. If stuff flows out, you have less. So this here is just the continuity equation. And this equation, well, velocity, time derivative of the velocity is an acceleration. So this here looks really like, but then because this is really the gradient of the velocity, so the relevant term here is this k squared psi, which because this is already a gradient, really this tells you acceleration of the velocity field is gradient of psi. So the psi field is effectively your Newtonian potential accelerating stuff. Okay, so the psi potential. So this here is just a standard acceleration equation, a continuity equation, Poisson equation, and some equation that tells you when the two potentials are the same and when not, but usually they are the same. Actually, you can see it, actually down here is specifically formatted. Okay. And the way you should think maybe about this, so I said before, when we look at the background, then we have one geometry variable, A, the scale factor, or H, A dot over A, and we have two matter variables, rho and P, and so we have two equations, and so we have one free variable, and we can think of this as P or W, and that tells us what the material is. And here now we have 6 variables. We have phi, psi on the geometry side. We have delta, v, sigma, delta, p on the matter side. And we have 4 equations. And so we have 2 quantities that are not fixed. And typically we say that delta p and sigma are at the perturbation level the variables that describe the material. And so, for example, cold dark matter has W, the pressure is 0, pressure perturbation is 0, and the sigma is 0. Radiation would have W equal 1/3. Turns out it also has delta P equal 1/3, and it has sigma equal 1/3 as well. Actually, it also has some other stuff, but that's beyond the. And so, okay. And so, so one approach that we will discuss tomorrow is that you can actually just try to measure this and then go and try to measure that. So, this is actually a really fancy approach. Anyway, and I have to question this totally else by now. Okay, great. But here I always take way too long. But this is really the basis of what we're going to discuss afterwards in the dark energy. So you may be wondering, why am I telling you all of this? But because I'm right now explaining you everything about dark energy, except I'm not calling it dark energy. Okay. So typically, for the evolution of the perturbations, you can approximately write it as a second-order equation of motion. And actually, this is again more or less an equation like this, except I have replaced the gradient of the potential. So it's again a second-order equation for the density perturbation. And so this is the acceleration of the density perturbation. This is again a friction term. But now, if I use the Poisson equation to remove the gradient of the gravitational potential, I can link it back to delta. So effectively, I have the gradient of the gravitational potential, but then I can use the Poisson equation, Laplace of the gravitational potential, like delta rho, to link it back in. Then I get an equation that, if I forget about the friction for a moment, has second derivative going like delta. And so what are the typical solutions of such an equation if we assume that the bracket is constant for a moment? Yeah, so they're exponentials, and if let's see, if this bracket is negative, then the exponentials should be complex exponentials or oscillations. Let's hope I get it the right way around. I'll let you think about it. And if the bracket is positive, then I get real exponentials, so exponential growth and decay. And so these are really the things that then can happen. So if this one is positive, then I get rapid growth. Actually, the friction will slow it down to power law growth, and this is the gravitational instability. So structure formation is unstable. You will form structure, but then because this is a k, so as k becomes larger, if the sound speed is non-zero, at some point this term will become important, and then that is pressure support. And so at this point, pressure will stop gravitational collapse, and instead you become some. You will have the. You will form some stable structure, and so this will be the G state. And that's a little question now. If now you try to invent, so this applies to any material, depending on the CS square, I should say, this is effectively delta P over delta rho. So if your favorite model has a negative CS squared, is that the problem or not? So what do you think happens if CS squared is negative? Do the fluctuations disappear? Do they grow rapidly? Or I have no clue. Okay, I'll give you 2 seconds to think about that. Okay, who thinks it's A? Who thinks it's B? Who thinks it's C or D, or who is on the C or D level, the rest? So you can just, so if the CS square is negative, then this means it's a positive quantity that on arbitrarily small scales becomes arbitrarily large. And so if you have delta double dot proportional to some large number times itself, that gives you an arbitrarily fast exponential growth. And so this is extremely unstable. This is so unstable that your model does not in general survive it. And so if your favorite model has a negative sound speed squared, it's basically dead. Okay, and so this is an example of a stability condition. Then when you do model building, you want to verify that your sound speed squared is not negative. Otherwise, your model is in deep trouble. So you see, we're actually now already model building at some level, except I haven't yet told you that we're also talking about dark energy. But we will get to all of that back. Okay, so I wanted to be here about 10 minutes ago. But so because effectively this is the end of the cosmology part, except as I said, we're already deep in dark energy. So at this point now, thinking of it as a cosmology lecture, we have our Friedmann-Lemaitre-Robertson-Walker metric, we have lambda CDM as a model, we have inflation for the initial condition, and this is actually extremely consistent with the data, except maybe H naught, but that's not what I want to talk about, and maybe some other main problems. Okay. And as we already said, we don't understand 95%. We have problems with the cosmological constant that I will explain now, and it has some other problems, but who wants to complain? But in principle, it's a model that works extremely well. And okay, so now let's go slowly towards the more detailed discussion of dark energy, where we will go back a lot to what I just explained. So let's quickly talk about what is the problem with the cosmological constant, and then we will go into action-based models and into unified models. And then at the very end, I will tell you what we know about dark energy today. Okay, so just to remind ourselves, so this is the plot. Actually, here this is someone asked yesterday about the BAO constraints. Okay, this is an older plot, but the BAO is cut about through like that, supernova like that. The difference is the redshift dependence and the CMB, and that's why we cut out this part. And this was good enough to convince the Nobel Prize Committee that the universe is accelerating, which led to the 2011 Nobel Prize. Okay, and so why, and since lambda is perfectly in agreement with the data, so why actually do we want to look somewhere else? And so then we can go to the plot. So there are two standard problems with it, and so one standard problem we can easily see in that plot. It's a bit like the initial conditions of the curvature, right? So the curve of the universe needs to be extremely flat at early times, and we would like something to explain it. And the cosmological constant problem is similar. If here the matter and the cosmological constant are of a similar size, as we go back into the past, the cosmological constant is very, very much subdominant. And so what set these initial conditions? It's actually worse, as I will explain in a moment. And the second point is, okay, since there are 3 powers difference in evolution between matter and cosmological constant, so why are we living exactly here? No, why? Because, so to go first to the coincidence problem, if you look at omega lambda, well, so the amount of cosmological constant relative to the total, well, in the past it was effectively 0. In the future it will be 1 forever, and we happen to live exactly here. And so there is only a relatively short time, so this is an exponential logarithmic scale, there is only a short time when we are actually able to see that there is both matter and the cosmological constant. So this is called the coincidence problem. Whether this bothers you, whether this should bother you is hard to answer. I'm not extremely bothered by it. I mean, the question is mostly why don't, because, okay, we can't really live here because we didn't really form structure at the redshift of 100. So we could live here, but at some point, of course, stars run out of energy, and then the universe becomes a very boring place. So there is not an infinite amount of space here either, but it's really kind of hard to say whether it's a problem or not. But people worry about it. But the main problem is really the observed amount of cosmological constant. Because the cosmological constant that we introduced by hand, it looks exactly like a vacuum energy that you get from virtual particles. Okay, I have to see when I have to stop. You just stop me, please, and I should. Okay. So when you look at like a vacuum diagram, that's basically just the particle-antiparticle splitting, and that corresponds just to momentum going in a loop. You can calculate, and the integral that you have to solve is this integral where you integrate square root of p squared plus m squared over momenta. And of course this diverges, so you have to cut it off at some scale. And so this lambda here, yeah, I really yell. Whenever I show this slide, I say I should change the notation. Unfortunately, the cutoff scale is generically called lambda, exactly like the cosmological constant. Has nothing to do with each other. So the lambda here is the cutoff scale. And so you get this expression. And this you also do when you have to renormalize any field in quantum field theory. And this works very well, and we can do quantum field theory. QED works extremely well. And we see also running terms in QED. These terms are there. But somehow, when we talk about vacuum diagrams, this cannot work. Because if it did work, then, okay, some of these terms we can in principle absorb into the raw lambda. But some of these terms depend, like they run, and so whenever, and especially also when you change, every time you change your cutoff scale, you also need to readjust your fine-tuning. And so your theory is not stable against any of these corrections. So every time your energy scale becomes higher than the mass of a new particle, you get new contributions from new particles, and you need to retune your theory. And this is considered as extremely problematic. And all of these scales, they are way above. All of these scales are at the mass scale at least. And so the observed scale of the cosmological constant now is milli-electrons volts. Electrons are half a mega-electron volt. LHC is a tera-electron volt. And so all of these should give huge corrections to the cosmological constant that you have to refine-tune basically for every energy. So this is just considered as extremely problematic. I mean, you have to see then, of course, that it doesn't really help. So typically theorists then much prefer to pretend that there is no problem. Basically, that it's exactly zero, rather than very, very large. So theorists would have less of a problem with zero than with a small and non-zero number. Okay. And so then at this point, maybe we can make a little list, okay, of possible explanations. And before we go to the dark energy modified gravity, here are some other ideas what it could be. Well, it could be that it is a cosmological constant, and there is some reason why it's small, and it's somehow connected typically with having many possible choices, and us only able to exist in the universes with a very small cosmological constant. So this is some combination of anthropic principle and typically string landscape. And I will not really talk about this because I don't have a lot to say about it. Maybe the right answer, but it's not. It kind of tells us very little. So this would be kind of the worst answer, I think, for most theorists. Then it could be that the data is wrong, but this starts to be very unlikely just because we have so much data and it's all very consistent. And then it could be that we misunderstand GR, because GR is a nonlinear theory. And in addition, we have been using, for our model, we have been using the cosmological principle, and so it could be that either we live in a special place in the universe, or it could be that we wrongly use GR, and the non-linearity in GR is much more important than we think. Okay, and so I will quickly discuss this first tomorrow, and then the other alternatives are that there is something additional in the universe that makes the universe accelerate, and that's what we normally call dark energy, and that's exactly the scenario we have discussed for inflation. So where you have some additional field, and then there we will look at different models of fields. And the other possibility is that actually our theory of gravity is wrong. So we know it mostly on small scales. It works very well. It's very well tested on solar system scales, but we extrapolate it up to horizon scales in the universe that are many, many orders of magnitude larger. And maybe on these very large scales, there are some modification of general relativity that lead to the observed, at least apparent, accelerated expansion. That would be called modified gravity. And I think
solving the cosmological problem, the previous.
Yeah.
So this is in the same category as, for example, getting a scalar field, a evolving field, in the sense that you are saying that in the end of the day, vacuum energy, whatever it does not gravitate. Because what I mean is that vacuum energy exists. We know that.
Yeah.
Right. So in this solving the problem using this possibility, you are saying that okay, it exists, but for some reason it does not gravitate.
Yes.
Right?
For all of these, for any of these, basically this one says there is no dark energy because the data is wrong. This one says there is no dark energy because it's some other physical effect. Okay, this one says it's dark energy but not the cosmological constant. So for all of these, in addition, lambda has to be 0. And that is actually, and why this would be 0, that's actually also a difficult problem. It's probably it's considered slightly less worrying than a small but non-zero lambda. But it is difficult because typically, so I was actually not really going into detail in that, but this is an important additional question because you have to be careful since we want to have inflation, and inflation is in principle also effectively a vacuum. Slow roll inflation needs the gravitational potential to accelerate the universe, so it's a bit like a temporary cosmological constant. And so if you are very good at making the cosmological constant not gravitate, you can easily kill inflation. And so you have to kind of not do it in the early universe, but do it in the late universe. And so already it's difficult to invent mechanisms that can do it. But we usually just pretend.
Yeah. What I'm saying is that, okay, suppose that you have lambda different from 0.
Yeah.
Right? But it just does not gravitate, right? So in principle, from 2 up to 5 is the same category, right?
They all need that, yes.
But in the case of inflation, we know that inflation ended at some point.
Yeah.
And it could not be lambda, right? Otherwise,
it would never end.
Never ends, right?
Yeah.
So we already had an accelerated expansion in the universe, right? We are having the second one. So the first one was not driven by lambda, so the second one in principle should not.
Yes.
It's more or less in this line.
Yes. I actually have that comment later. Exactly that comment later. And for me, this is actually also one of the motivations why it's interesting to look at this. So I'm going to argue that neither of these really work, and so it should be somewhere there. And then in addition, inflation I think does give us a good argument that it's not so unnatural.
Questions?
Quantum gravity can be a possible explanation?
Well, but more in the sense that it would give us, typically quantum gravity is a high energy. One of the problems of using quantum gravity for dark energy is that it's typically a high energy phenomenon, like an ultraviolet modifications. So like on very small scales, like Planck scale, you modify gravity. And but this what we have here is an infrared problem. So then you need to somehow make your quantum gravity solve something in the infrared. So that's why they usually quantum gravity models, they usually have more an indirect connection by proposing some field theory that then can be subsumed somewhere here. But
questions?
If the spin of data is wrong, how do we explain the other data sets?
Yeah, exactly.
Like DAO?
Yeah. So the answer, so it's a bit more subtle, right? Because we have BAOs and CMB plus BAOs give the constraints that we need. And the supernovae, if the supernovae are wrong, the BAOs would also have to be, or they would have to show something else or also be wrong. So you need to be fairly creative to still create models where you can do. So some people are still fairly creative, and they do come up with scenarios because then you need to argue that you also understand some other physical mechanisms in the early universe that set the peak scales. So yes, that's why I also don't think it's very convincing. But if like there are some papers by Subir Sarkar, Alain Blanchard, and probably some others where they can kind of, I mean, the question is always how many things do you have to break to still make it work, and over time you need to break more and more things. So, I mean, you also need the very massive neutrinos and many of, so yes, so it's kind of, the question is a bit how many data sets do you have to disbelieve in order to make it work? And I think we are really in the limit where it seems unlikely.
Hi, thank you for the lesson. And I want to know what's the relationship between the dark energy and the Higgs field?
There are not many scenarios that really. I mean, I recently got that question, so I actually quickly looked into it, but only quickly. So there are not a lot of papers that try with more or less success to create such a link. I mean, the Higgs field seems to work fairly well for inflation. But that's then typically, actually, it's a bit like a modified gravity Higgs field because you need a non-minimal coupling. But I only found about 2 or 3 papers that look at the link between Higgs field and dark energy. So this seems to be quite difficult to realize, to create such a model. So a priori, nearly no one can use the Higgs field to create dark energy.
Thank you.